differences between males and females in endurance running. So this project was conducted here at the University Jean Monnet of Saint-Etienne and was funded by Decathlon. This presentation will be divided into 4 parts: an introduction, 2 main parts where I will detail the 4 studies conducted during this PhD, and finally, a general discussion and perspectives. I will start with an introduction where I will talk about sex differences in participation in running events, and then I will talk about sex differences in endurance running performance. I will start with a bit of history because females were not always allowed to officially compete with males. So for example, there were no females in the first Olympic Games. They had to wait until 1928 to participate to the first track and field events. The first woman who officially competed a marathon was Catherine Schwitzer in 1967. The first Olympic marathon for females was in Los Angeles in 1984. And even if it's not running, it is interesting to notice that the 50-kilometer walk has never been Olympic for females. These 2 graphs represent the female participation in endurance running events. So on the left, on the road running events. This study on the left was performed on more than 70,000 road race results around the world, from the 5 kilometers to the marathon distance. We can observe that since 2018, the rate of participation of female has reached the 50%. On the right, the figure represents the participation of female in trail running events. And you can see that the female participation is much lower in trail, despite an increase from 18% in 2013 to 26% in 2019. These 2 graphs also represent the female participation in endurance running, in trail running, as a function of the race distance. So each point corresponds to a single race. And so the top graph corresponds to the races, trail races in France, and the bottom graph around the world. And you can clearly observe a drastic decrease of the female participation with increasing the race distance, with a participation of females being less than 10% for events longer than 100 kilometers in France. Indeed, the female participation also depends on the geography. You can observe a female participation of 15 to 20% in France for trail races lower than 80 kilometers. And this sex differences, it's almost twice bigger in North America. This graph represents the sex difference in endurance running performance. So first on flat running events from 100 meters to 24 hours, which correspond to around 300 kilometers. And you can observe that the sex difference in performance is around 8 to 12%. On trail running, the sex difference in performance is bigger, between 20 to 25%, at least until 400 kilometers. You may not know the common point between these 4 female athletes. They all won an ultra trail running race overall. So in other words, they finished their race before the first male. It is one specificity of ultra trail running. It's one of the rare disciplines in which females sometimes outperform males overall. So we can wonder, are females reducing the gap with increasing the race distance? And it spikes the interest of scientists, but also and led to many press articles, such as those ones. Why do women win ultra? Why women are better at ultra running? And even a very recent article in the French press, Quand les femmes surpassent les hommes. However, caution has to be taken when interpreting the results. First, it depends on how the question is examined. So if you look at the top graph here, it is the sex difference in performance when calculated the difference with taking all the males and all the females of each race. And indeed, in this case, it seems that the sex difference in performance seems to decrease with increasing the race distance. But if we calculate the sex difference in performance with taking the first male and the first female of each race, the sex difference seems constant. Second, it also depends on the participation rate of female, of course. in a race where there are 95% of males, females have less chance to best perform. And third, even there is no clear scientific evidence, it is possible that the race profiles, such as the elevation change, or the technicality of the terrain, or the conditions, such as the temperature, could have a sex influence. And may also explain the difference observed in road race results compared to trail running events. Indeed, there are sex difference between the male and the female endurance runner. So I won't go in detail in this figure now, but it will be the common theme of this presentation. So to cite a few, first in blue, you can observe sex difference in biomechanics. It is also well known that females have a lower maximal oxygen uptake compared to males. Conversely, females have a greater proportion of slow twitch fibers, a better ability to use the lipids. And we also observed less neuromuscular fatigue in females compared to males. From these main differences reported in the literature, we clearly observe a lack of sex comparison on trail runners, under fatigue conditions, and on the influence of footwear. So there is almost no study comparing the effect of the shoe on males versus females. So this thesis project has two main objectives. First, a fundamental objective where we try to characterize the male and the female trail runners in both non-fatigue and fatigue conditions, will be the topic of the second part of this presentation. An applied objective where we looked at the influence of the footwear on running biomechanics. Let's move to the second part of this presentation about physiology and fatigue. So first, we'll look at the characterization of the male and female trail runners. So what is trail running? So the International Trail Running Association defines trail running as a pedestrian race taking place in a natural environment with a road section being lower than 20% of the total race distance. They also distinguish trail from ultra trail with a distance of 80 kilometers a race. Trail running induces a specific adaptation that are different than the one induced by classic road running. I won't detail it now, but it will be the topic of the defense, one topic of the defense of my colleague Fred in 1 month, also here in Saint-Etienne. In just under 10 years, trail running has moved from an amateur practice to a major outdoor activity, and flagship races have emerged. For example, UTMB, which is probably the most famous trail running events in the world. National and world championships have also been organized, which probably raise the level of the top-level athletes. More and more good runners belong to teams and get contracts with sponsor brands. Trail running depends on a lot of external factors, such as the altitude, the elevation change, the temperature, or the technicality of the terrain. So altogether, these factors make the analysis of the determinants of trail running performance very complex. This figure reports the main indicators of trail running performance reported in the literature. And to cite a few, the importance of uphill coastal running, of VO2 max, maximal oxygen uptake, or lower limb strength or power. The study one that I will detail just after is part of a bigger project who aim to look at the influence of the discipline, trail versus road runners, and the level of performance of the runners, so elite versus non-elite runners, on the cost of running, biomechanics, and neuromuscular characteristics of male and female endurance runners. So for this study, we tested more than 70 runners, including the national team of trail and marathon. We tested them both in Saint-Etienne here at the lab and during national training camps, both in France and also in Portugal for the elite athletes. The specific aim of the study one was to compare male and female trail runners of different levels, so elite versus experienced runners. It was the first study that compared male and female trail runners, including data on top international athletes. So for this study, we had two groups. experienced runners who had at least one trail race objective in the season. They were training at least 3 times per week, and they were training for trail running competition only. We also had elite athletes. So the ITRA defined a performance index which allows to characterize athletes as elites if they have a score higher than 700 for females and 825 for males. You have it here. About our experienced runners, they had a performance index between 500 and 700. It is also very interesting to notice that both females and both male and female teams of trail were world champion the same year as we performed the study. The protocol lasted around 1 hour and 15 minutes. Today I will present the parameters that are in blue. So the cost of running and the biomechanics in free running conditions, maximal isometric and dynamic strength, and maximal power. The cost of running was assessed using a portable gas exchange analyzer. Here are the results of the cost of running in the free running conditions. So for the rest of this presentation, females will be represented in red and males in blue. And we can observe a significant level effect on the free running condition with elite on the left had a lower cost of running compared to experienced runners. It is well known that cost of running is very important for the performance in classic endurance running. It is less clear in trail, with studies showing no link with between performance and flat cost of running, or studies showing only a link with uphill cost of running. Even if our study does not allow to make a direct link with performance, it seems that there is a gap between elites and good trail runners in this parameter, in cost of running. We did not observe sex differences on this parameter. The running biomechanics were assessed using an optojump placed on both sides of a treadmill in order to assess the fly time and the contact time. About the level effect, we observed a greater step frequency in experienced runner compared to elite. So the step frequency was assessed in a step per minute. And it is possibly the result of biomechanical adjustment, because experienced runners had to maintain a higher relative speed relative to their maximal aerobic speed compared to elite. We also observed lower step frequency in females compared to males and lower contact time. So as the level effect, it can also be the result of a higher relative speed in females, and it can also be the result of morphological differences between males and females. The literature reported that elite runners self-optimized their step frequency in order to be the more economical. And the results of this study showed an interaction effect, and we did not observe. This graph represents the step frequency of elite runners only, so of male and female. We did not observe differences in the step frequency in flat condition, but in uphill condition, female had a higher step frequency compared to males. So it is possible that in this specific condition, elite runners differently self-optimize their step frequency. For females, we've choosing higher step frequency compared to males. These are the results of the neuromuscular characteristics. So first, on this slide, I will present the level effect, the level of performance effect. We observed greater knee extensor strength in elite compared to experienced runners, but lower knee flexor strength, and we did not observe any difference in hip extensor strength. Through this study, we assessed the power torque velocity profile. So we asked the participant to perform 2 7-second sprints on a bike at 2 different loads. So why do we choose a bike? To ensure that the participants were giving their best, and also because it requires less technical skills compared to classic sprint running or to squat jumps, for example. These are the results of the power torque velocity profile. So elite athletes are represented here with the dashed lines and experienced runners with the solid line. The curvilinear curve represents the power curve, and linear curve, the torque velocity profile. Interestingly, despite we did not observe any level differences in maximal power, we observed a different mechanical profile between elite and non-elite, with elite showing greater force production capacities, but lower velocity production capacities. Now the result of the main sex effect. Not surprisingly, we observed that males had a greater knee extensor strength, greater knee flexor strength, but there were no sex differences in hip extensor strength. Concerning the power torque velocity profile, we observed greater force production capacities in males, greater velocity production capacities in males, and then greater power production capacities in males. But interestingly, the mechanical profile of male and female trail runners was similar. So we observed a downward shift of the male curve to obtain the female curve. Let's go back to the figure of our elite runners, which represent the indicator of trail running performance. This study confirmed the importance of uphill cost of running, of knee extensor strength. We also showed that elite had a lower cost of flat cost of running and lower step frequency compared to non-elite. Our study did not show any level differences in the lower limb power, but we observed greater force production capacities in elite compared to non-elite. It is probably the result of more specific strength training, and also because they are training more with possibly more elevation change compared to non-elite. And this was counterbalanced with lower velocity production capacities, which is probably the result of different muscle tissue characteristics and especially greater proportion of slow twitch fibers in elite compared to non-elite. Let's go back to the summary figure presented at the beginning. This study showed that only also on trail runners, there were no sex differences in running economy, greater step frequency in females, and lower contact time in females. We also showed that elite trail runners had a difference in their step frequency, with female elite runners showing greater step frequency compared to males in uphill condition. We also reported lower production capacities, but a similar mechanical profile. The second part of this second part the aim of this part was to better understand and characterize the occurrence and the etiology of neuromuscular fatigue in males and females following prolonged trail running. Neuromuscular fatigue can be defined as a progressive change that occurs in the central nervous system, or central fatigue, so above the neuromuscular junction, and or the muscle, or peripheral fatigue, below the neuromuscular junction, resulting in a force output that is less than anticipated for a given voluntary contraction or stimulation. The literature reports a strength loss following prolonged running exercise. So this graph represents the knee extensor strength loss as a function of the running exercise duration. And you can observe that the knee extensor strength loss seems to increase with increasing the duration, at least until 1,000 minutes of exercise. The strength loss was explained by central parameters, such as a deficit of voluntary activation, or peripheral parameters, such as a decrease of sarcolemmal excitability, or alteration of the excitation-contraction coupling. Concerning sex differences in neuromuscular fatigue, so most of the literature was performed following single-joint fatiguing tasks. And the literature is pretty clear, showing that females are less fatigable than males following both isometric and dynamic exercise. What about following running fatiguing tasks? There are, to my knowledge, only 3 studies comparing sex differences following running. And 2 of them showed greater neuromuscular fatigue in males compared to females, and 1 study showed no sex differences. So there is no consensus. There is a very low number of studies, and the tasks were very different, because it was treadmill running on this one, ultramarathon and the road running on this one, and the exercise duration were completely different. Then the aim of the second study of this PhD was to further characterize sex differences in neuromuscular fatigue by examining various running distances. This study has been published this year in MSAC. For this study, we recruited more than 75 runners. From these 75 runners, we were able to make 18 pairs of male and female at the end of the race. So there were these pairs of males and females were matched relative to their performance, relative to the first male and the first female of their specific race. The participants were tested 1 or 2 days before the race and were tested right after the race. So they crossed the finish line and they directly had to move to the lab to be tested again. The participants were further divided into 2 groups: short distances below 60 kilometers and long distances above 100 kilometers. The neuromuscular assessment was a classic neuromuscular assessment with maximal voluntary contraction with superimposed stimulation, and stimulations on the relaxed muscle. And it was done on both knee extensors and plantar flexor muscles. In order to obtain peripheral fatigue, we looked at the amplitude of the peak twitch, single twitch, and in order to obtain central fatigue, we calculated the voluntary activation with the following formula. These are the results of the maximal voluntary contraction. So it is important to note that on those graphs, all race distances were pooled. And we observed a greater force decrease in males compared to females in the knee extensors. But despite it was not significant on the plantar flexors, it seems that there is the same trend. This result, so the strength loss was greater in males, and this result is in accordance with a previous study from our group from Tennessee 2014. But contrary to our hypothesis, these results were independent of the distance. We did not observe sex difference in central fatigue, as reported here by the voluntary activation on both knee extensors and plantar flexors, and this result is also in accordance with the study of Temesi. Concerning peripheral fatigue, our result showed time-sex-distance interaction on the plantar flexors. So if we go deeper in the analysis, we reported a greater decrease in the peak twitch amplitude in males compared to females. You can see here a decrease of 24% of the peak twitch in males compared to 10% in females. Temesi and colleagues observed similar results following an 110-kilometer race. It can be explained by sex differences in fiber type, because we know that females have a greater proportion of slow twitch fibers. It can be also explained by sex difference in substrate utilization. It is possible that males were more glycogen depleted compared to females, and it can also be explained by sex difference in race effort. Indeed, in this study, we asked for the competitive intention of our participants. So in other words, how competitively oriented they were, if they performed their race in a more competition mode, or if they performed their race more for fun. The results showed that on short distance only, males were more competitively oriented than females, and it was not the case on long races. So it is possible that males stretch their limit deeper, and it can, in part, explain the sex differences observed in peripheral fatigue, so greater peripheral fatigue in males compared to females. To conclude on this study, following ultra-endurance trail running, relative to the same level of performance, female experience less neuromuscular fatigue compared to females compared to males. And contrary to our hypothesis, sex differences in neuromuscular fatigue do not seem to increase with the race distance. This study also brings a new result on the competitive intention of our participants, and I think that these parameters should be further investigated. This is the summary figure. So this study showed that on following trail running races, female experience less neuromuscular fatigue compared to males. We also reported an influence of the distance, with males showing greater peripheral fatigue following short distances compared to females. And we also reported a possible psychological sex differences with the parameter on the race intention. Let's move to the third part of this presentation about biomechanics and footwear. So the aim of this part was to investigate the influence of key foot parameters on running biomechanics. There are sex differences in running biomechanics, so I already talked a bit about sex differences in spatiotemporal parameters with the study 1. There are also sex differences in running kinematics, and the literature is pretty clear, showing that most of these differences appear at the hip and the knee level, and in both the frontal and the transverse plane. For example, female exhibit greater hip adduction, greater hip internal rotation, and greater knee abduction. It has been suggested that these results are, these observations are the results of possible anatomical sex differences. So for example, females have a greater Q angle. So as illustrated here, the Q angle is the angle between the femur and the tibia. Females also had a greater pelvis width related to the length of the femur. However, the extent to which morphological differences contribute to sex differences observed in the literature is not clear yet. Through this presentation, we already talked about sex differences in muscle strength, in morphology, but there are also sex differences in running-related injuries, and also sex differences induced by the footwear habits. So for example, females who wear high heel shoes daily, it induces structural adaptation at the Achilles tendon level, for example. Altogether, with the sex differences observed in running biomechanics, would lead to different shoe requirements. So through this thesis project, we looked at the influence of two main shoe parameters, the shoe drop and the shoe longitudinal bending stiffness. The method used to assess the running biomechanics in this study were the same, in this PhD were the same for the study 3 and 4 that I will detail just after. So we assessed kinetics and kinematics of running. For the kinetics, we used a 6-force platform. So this picture is taken from the lab just in the other building. And in order to assess the kinematics, we had 2 camera motion analyses. For the study 3 and 4 that I will detail just after, before testing each shoe condition, participants had to warm up in order to get familiarized with the shoe and also in order to stabilize the mechanical shoe properties. So first, I will talk about the influence of the shoe drop on running biomechanics. What is the shoe drop? The shoe drop is the thickness difference between the heel and the forepart of the shoe. And this parameter has been shown to have a significant influence on running biomechanics. So it was reported a decrease of the foot ground angle with reducing the shoe drop. So the foot ground angle at contact. So if you decrease with a flatter shoe, you decrease this foot ground angle, as illustrated in the picture here, even if it's a bit exaggerated on this picture. All these studies were conducted in males. Then the objective of the study 3 was to investigate the effect of the shoe drop in running biomechanics, on running biomechanics in female runners. For this study, we recruited 15 recreational female runners. They had to test 3 shoe conditions in a random order. So a shoe condition with a 10 millimeter drop, a shoe with a 6 millimeter drop, and a shoe with no drop. For this study, participants had to run at their preferred running speed. We performed 2 different statistical analyses, a classic one-way ANOVA on the key parameters of running biomechanics, and a statistical parametric mapping with adding a temporal component to the analysis. These are the results of the classic ANOVA, and our results show that showed a lower foot ground angle and lower ankle flexion angle with the zero drop shoe compared to the two other conditions. Despite clear methodological differences with the study of Nicolas Chambon performed in 2015, it seems that we observe the same trends in this study performed in males. Now, the results on the influence of the shoe drop and lower limb joint moments. So the result of the statistic of the SPM reported a lower knee joint moment in the zero drop shoe condition at the middle of the stance phase of running, stance phase duration, sorry. Conversely, the results showed a greater ankle joint moment during the first phase of the stance phase with the zero drop shoe compared to the two other conditions. So this study was the first that highlights the joint moment role distribution induced by shoe drop changes in females. From those results, we can advise lower shoe drop for runners with knee pain or knee weakness, and conversely, a higher shoe drop for runners with ankle pain or ankle weaknesses, or for females who wear regularly high heel shoes. I will now detail the study 4 of this thesis project about the influence of shoe longitudinal bending stiffness on running biomechanics. So the shoe longitudinal bending stiffness, or LBS, this shoe parameter has been at the top of the actuality because of its supposed influence on endurance running performance. You also the performance of Eliud Kipchoge, who ran the marathon in less than 2 hours last year, I think. And one part of this exceptional performance was explained by the shoes that he was wearing. And especially one parameter of this shoe was the very high stiffness of the shoe with the carbon plate placed inside the midsole of the shoe. The literature showed a significant effect of the shoe longitudinal bending stiffness on both energetics and biomechanics. So for example, on cost of running, on ground reaction forces, on lower limb walks, and lower limb joint moments. All the studies here were conducted in males. Therefore, the aim of the study 4 was to look at the influence of the shoe longitudinal bending stiffness on running biomechanics of male and female recreational runners. In this study, we recruited 15 males and 15 females. They were all recreational runners. They had to test 3 shoe conditions in a random order, and they had to run at 2 absolute speeds, at 10 and 13 kilometers. In this presentation, I will only present the result at 13 kilometers per hour because of time reasons. About the shoe conditions, they did not differ in terms of mass. And from a standard shoe, we obtain a flex condition with making flexion grooves into the midsole. And to obtain a stiff condition, we added a carbon plate just above the outsole. This slide is about the main sex effect, so independent of the shoe. And we observed sex difference in kinematics. So we observed, you can see in red, that females showed greater hip and knee flexion at impact compared to males. It is a possible strategy to attenuate shocks because of, again, greater relative speeds in females. These kinematic differences possibly explain a lower maximal vertical force observed in females. And in order to maintain the greater relative speed, females had to produce a greater propulsion force, so in the anterior-posterior ground reaction force, compared to males. Now the results about the main sex-shoe interaction. So this graph represents the results on the MTP angle amplitude. So it is the amplitude of the metatarsophalangeal angle, MTP. So it is this joint. So it's the amplitude of this angle during the stance phase. And we can observe that there were no differences in males between the free shoe condition, but females were it is possible that females were less able to bend the stiff shoe condition compared to the two other conditions. How to explain this result? So it is a possible result of lower force production capacities in females or lower body mass. Nice. Sorry. This graph represents the result on the MTP joint power along the stance phase in both males and females and in all shoe conditions. From the power curve, we can obtain the work produced at the joint. The work is calculated with the area under the curve. And here you have the negative work, which is the energy absorbed, and the positive work, which is the energy generated by the joint, so the energy important to allow a forward propulsion. So we'll focus on this specific parameter now. So this is the positive MTP joint in the free running in the free shoe condition in males in blue and females in red. And interestingly, with increasing the stiffness of the shoe, there was no difference between the flex and the standard in males, but the increase appeared between the standard shoe and the stiff condition. Whereas in female, the increase was already reported between the flex and the standard shoe, and then no difference between the standard and the stiff shoe condition. So we can suggest a different biomechanical threshold between males and females, with increasing the shoe longitudinal bending stiffness. To conclude on this study, it brings new data on male versus female endurance runners in response to modification of the shoe longitudinal bending stiffness. With increasing the shoe LBS, we observe a decrease in MTP joint angle amplitude in females only. We observe different biomechanical thresholds, so we can wonder if males need a stiffer shoe in order to obtain the same adaptation as the one observed in females. And it was a possible limitation to our study. So this graph represents the shoe longitudinal bending stiffness of our free shoe condition. So it's the male shoe condition. And the blue bars represent 30 other shoes of the market. And we placed our condition within the shoe of the market. And we can observe that the stiff condition is probably not stiff enough compared to the stiffest shoe of the market. Finally, the general discussion and the perspective of this PhD project. So at the beginning of this presentation, we talked about female outperforming males in some ultra-endurance running events, and leading to many press articles, and this curve representing the sex difference in performance, and with observing females possibly outperforming males over a very long distance. So we can wonder, will a female ever outperform males at UTMB, which is the most famous trail running event in the world? This figure is an overview of the factors that could have a sex influence in endurance running performance. So in short events, the sex difference in performance is mainly explained by a greater VO2 max in males compared to females. But the importance of VO2 max seems to decrease with increasing distance. And it is true that over a very long distance, females have some physiological characteristics that can give them an advantage. For example, a greater proportion of type 1 fibers, a better utilization of fatty acid, and less neuromuscular fatigue. However, several important of male characteristics, such as VO2 max, better oxygen carrying capacity, and the lower body fat percentage, make it unlikely that the fastest woman will ever outperform the fastest males. Moreover, given the level of the best male on this particular race events, it is unlikely that it would ever happen. Also, if we look at these graphs, which represent the sex difference in performance in the most famous ultra trail running events in the world, we can see that the sex difference in performance it's closer than 20% rather than seeing a female outperforming the males. And it is also why the performance of Courtney Dauwalter at the UTMB this year is pretty impressive, with a sex difference in performance of 8%. So the point will be around here. Through this thesis project, we added many points to the existing literature. So this graph represents the knee extensor strength loss as a function of running exercise duration, with the black points between data in males, the gray points data in females, and when it's circled in red, it's the new thesis findings. And we can interestingly observe a downward shift of the female curve, the downward shift of the male curve to obtain the female curve. So in other words, for the same running exercise duration, we observed less muscle strength loss in females compared to males. It led to many perspectives. So are these the results of psychological aspects? So are female pushing less? We already talked about the competitive intention during this study 2 of this project, and I think it should be further investigated. Second, it is possible that there are sex differences in pacing related to the profile. From our result on the UTMB, we looked at the speed at which males and females perform the downhill section. And we observed that males were running faster in downhill section in absolute, but also in relative, so relatively to the main speed of their race. So this result is interesting, knowing the importance of the intensity at which we perform downhill section on the peripheral impairments. So I can partly explain those results. And then all the point of the literature were performed in good or experienced runners, but we have no data on elite runners. So what about neuromuscular fatigue in elite? There are some specificities of the elite which can make us think that some of these parameters can limit the level of neuromuscular fatigue, such as greater resistance to muscle damage, but others could accentuate the level of neuromuscular fatigue. So for example, as just said, we know that elite are running faster, especially in downhill, and that could lead to greater peripheral impairments. To make the link between fatigue and the shoe, we performed this study at Les Templiers in 2018, where we were interested in if the fatigue of the shoe during a trail race, so for this specific study, it was a 40-kilometer race, if the fatigue of the shoe, so the deterioration of the mechanical properties of the shoe, will significantly alter the biomechanics of the runner, the biomechanics of the runners. This study had some limitation, and we did not observe any interaction between the fatigue of the shoe and the fatigue of the runner. But this study was original and was a field study. Then it can be interesting to replicate this study in a more controlled environment. And so also, we can wonder if the sex can have an impact on the deterioration of the shoe during a race. It is possible that we observe less impact males because they are taller, or it is also possible that we can observe lighter impacts in females. And what would be the difference of those two aspects on the deterioration of the mechanical properties of the shoe? And finally, should the mechanical properties of the running shoe be adapted to females? Investigating the effect of the footwear on biomechanics is very complex because it depends on the interaction between the runner, the task, and the environment. And most of the literature is done in very acute conditions, so in a lab when running 15 meters. But what happens when running 1 hour or in downhill on uneven surface? So the the main goal for the shoe company at the end will be to individualize the shoe to the runner in order to prevent injury or in order to improve running performance. And adding inter-individual measurements is a work that we initiated at this lab with measuring plantar flexor musculotendinous stiffness in our runners. We also did some plantar flexor and two flexor muscle force production measurements. Then, to answer to the initial question, despite the results of the study 4 suggest sex-specific adaptation to changing the shoe longitudinal bending stiffness, there is a clear lack of data, and we don't know if the results observed are a real sex effect or if it depends on inter-individual variation, such as force production capacities, or body weight, or fat mass, etc. Thank you very much for your attention.